Thank you, Nicole. Let's get Sofia back on stage as well. Yeah. And we have microphones for you as well in a couple of minutes. But Nicole, you mentioned the idea that the energy surrounding entangled particles can be used to lift small weights. Can I use it to charge my phone?
Not quite yet. At the moment, quantum thermodynamics has been at the stage of fundamental discovery, and we're now starting to pivot toward practical applications. For instance, I recently collaborated with a lab in Sweden on a quantum refrigerator that would actually assist a quantum computer. So after a quantum computer has performed a computation, the qubits are used up, they need to be cooled down even more, and this quantum refrigerator can do that, according to one metric, better than some of the best known techniques.
Now, when we think about things like quantum engines and batteries, what is the time horizon to make them practical, usable elements of, I wouldn't say daily life, but our current reality?
I probably shouldn't make a prediction about timelines, but this first practical experiment that I mentioned happened last fall. It was performed by an experimentalist at a university that is building a quantum computer from superconducting qubits, so very cold quantum circuits. And we came up with this idea in part because he said it could be useful for him and his colleagues as they are building and using this quantum computer.
Sofia, you work in quantum, but you also work on artificial intelligence and machine learning. Tell us about the bridges between the two.
That's a very nice question. So the point is that for many years, the first algorithms quantum algorithms that people started to know and try to use proved that you could actually accelerate the algebra very easily, or with very much. And most of what you do in machine learning, at least classical machine learning, the way we used to do it a few years ago, not ChatGPT today, just so we're clear, that's mostly algebra. And so very early on, people started to think, okay, maybe we can use quantum computer to speed up machine learning. Now, the point is that machine learning is actually useful when you can run it on a lot of data. And that's actually something that we cannot do so easily today on quantum computers, mostly because of the limitations that computers have now, their size, and all the engineering that's needed to actually load classical data on a quantum state. So this is a very big challenge. But other than that, there are other things that quantum computing can do for machine learning. And one of the things that is, I think it's most fascinating is the fact that because we are using quantum state and because we are building systems that learn how to describe the data in a quantum space, then you can think of building models that are more powerful, okay, that are able to represent data sets that are more complex than what you could with a classical network. So there's two aspects. I would just like to say that this is something that already exists. So it's not something for which we need to wait a long time.
So you mentioned before the future collider of CERN, which is going to be much larger in size, but also much more productive in data.
Yes.
It's gonna create huge amounts of data, which don't seem to be manageable with current technologies. So you said that we're looking into quantum as one possibility for that, with other potential options. But will the technology arrive fast enough?
So the next generation LHC is actually very close in time. We are talking about 2030 something. So this is called the high luminosity LHC. It is unlikely that we will be able to solve problems at the LHC using a quantum computer, at least at the scale we are thinking of, people typically think of.
So what you're saying is quantum is developing much
It's a longer time scale, or we need to think of it for very specific problems. That is something we will be able to do.
Okay. Let's see if we have some questions from you here in the audience. So
I don't see.
There's a hand raised right there. Can we get keep your hand up so she can see you? Yes. Stand up and ask your question, please.
Hello.
Now we go.
Okay, it's a question for Sofia. My name is Marco Palumbo. I work for Inflection. We are also a quantum computing a company. So the question is about the vision for CERN. Do you, as a user of quantum computers, will you be building one
Okay.
If you're going to build
Yes.
one, which platform are you going to go for?
I can tell you right away, we're not going to build a quantum computer, at least not in the next QTI phase, but we are going, so this all work started for us as users. Now we are also very well aware of the fact that a lot of the things we do at CERN are expertise that we can use to improve quantum technologies. So that is something that we want to do. So we are going to study systems of qubits. We are going to study how, for example, to improve the way we read information out of them, for example. We are going to study how we can characterize their behavior, to understand how stable they are, to understand how to best account for these problems that are related to the technology still and the fact that it's a quantum state. But our main goal is to understand the relationship between quantum and physics and high energy physics. This is the core of the investigation.
Yeah, no, thanks. That makes sense. Are you working mostly with the superconducting people? Are you testing, across?
Yeah. So there are. So this is. I'm not sure how clear it is. The fact that there are many different ways you can build qubits. You can build quantum computers. Nicole very nicely explained to you what is the concept behind the qubit. So there are many different technologies. Superconductors are a way of building qubits. We are working on we are using superconducting computers, but we're not necessarily going to focus on that technology only. And the reason is that the technology is developing very rapidly. There are many different options, and there are advantages and disadvantages at looking at different approaches to qubits, let's say it that way. And there are also advantages depending on the task that you have in mind. One specific technology could be better suited to solve a specific problem. And so we don't want to focus on only one direction.
Is there one more question? We have time for another question. Not the case. Yes, here. Wait for the microphone, stand up.
Or shout.
Does it work? Okay.
Yeah.
Okay, I'm a regular university student, so maybe my question will not be on level, but I have a question for Nicole that was talking about the quantum fridge and quantum batteries and all those stuff. If I understood correctly, they need to work the entanglement phenomenon, no? To produce then the information that gets deleted to get the work.
Some of them do. There are lots of different quantum phenomena, such as superpositions, entanglement, even more things that we didn't talk about. And some of these technologies do take advantage of entanglement.
Okay, so, but the thing is that I guess that to get to the low temperatures needed for this phenomena to to appear, you need to use a lot of energy in the first place, no? To get to those low temperatures. So how can you get then a net positive work to process something else?
Yes, that's one of the reasons why I said that you can't at the moment use quantum engines to charge your phone. So far, we have done a few things. We've designed quantum engines and other quantum thermal machines and shown that according to some metrics, they can outperform their classical counterparts. This is very fundamental work. Then, in part because I wrote that book and had this conversation with this experimentalist I mentioned, we started thinking more about really how to take these quantum thermal machines that are great in principle and make them actually more useful, more in the spirit of the Industrial Revolution. So we recently embarked on this research program of autonomous quantum machines. This quantum refrigerator is going to be placed inside one of those giant refrigerators that I showed you. That will already be cold because, for example, these folks at this university in Sweden want to perform a quantum computation. So if you stick your quantum refrigerator inside of that refrigerator, the classical refrigerator, it'll already be cold. You won't have to spend you'll have to spend negligible extra energy on cooling down your quantum refrigerator. And then we can give it access to kind of a free energy source, just basically the surroundings, so that it can kind of extract its own energy in order to cool down the qubits. So we're looking for these very specific situations in which we have an environment that's already cold, and we can just slide a quantum thermal machine in there like this refrigerator that will do its own thing. So far we have this application, and we're looking into more, as well as other research groups around the world.
We're going to come back to the question of energy use after the next talk. Okay?
Thank you.
Thank you. Nicole, Sofia, thank you very much.
Thank you. Thanks for the question.